Okay, good morning, everyone. Welcome to the today's class. Today, we would like to discuss about lecture number 13. Okay, we discuss about registers and counters. Verilog modeling of registers and counters we have been discussing about. So in the last class, we have seen that universal shift register, 4-bit universal shift register, right? Universal shift register. Okay, so how do we design the universal shift register that I have mentioned in this way? Okay. Okay. So what is its functional table? What is its functionality? So the functionality is depicted here. I will also copy this one. Okay. This is where we have used this one. Okay. So it's my output. This is actually the output is, for example, Q, 4-bit of Q, right? Q value. It's a 4-bit value. So when the selection line is 0, 0, the circuit has to produce the output called Q. Q is arithmetic Q3, Q2, Q1, and Q0. Okay, so therefore it has to produce. It must allow the parallel loading of the information. That means whatever the externally available data is there. I think I see better. I'll write it here in this way. It's a 4-bit universal shift register. It has got 4 outputs, 1, 2, 3, 4. Its names are Q0, Q1, Q2, Q3. So these data will be assigned by 4 input data of D. Okay, so D of 0 will be D of 0 is assigned to Q0, D1 is assigned to Q1, D2 is assigned to Q2, D3 is assigned to Q3. This is what happened if the selection lines are 0, 0. Okay, yes, you'll write 2-bit size I'm writing. Okay, so this is what happened first of all. Okay, this is the first operation. What is the second operation? The second operation is if selection line is 0, 1, shift right operation has to perform. In order to perform a shift right operation, that means that what we observe that um, 1, 2, 3. Okay, shift right operation means this position is filled with shift right data, shift right input. Okay, suppose some data will be added there in that one. So for that one, I'm going to use one extra terminal that is called SR, shift right data. Okay, so only this particular portion only which will be occupied, right? This portion only. Okay, fine. And the shifting has to be performed according to the diagram that is shown here. So okay, so a simple notation. First of all, this value will be there. So SIN, or in this case, it is called SR now. SR will be occupied the MSB bit position, and the Q3 is generated by here. That will be occupied. That will be placed here in this one. Okay, the Q2 is placed here, and Q1 is placed at this portion. Now it will produce an output called this one. Therefore, whatever the SIN is there, that SIN will enter into this one, and it is shifting from the device to device, something like this. Okay, it is simply a shift right operation. Agreed? Okay. So if it is a shift left operation, for example, I'm going to consider another data input that is called SL, shift left. Of course, we can use it SR also, a simple a control signal, nothing else in it. So data field signal. Okay, but I'm taking additionally another signal. Okay, so for that one, what I'm doing here instead of SI, what I can do here is that I will use SR. SL, sorry, SL. Okay. So in this configuration, what we'll do, so the LSB bit is filled with this data. LSB is filled with this particular data. Okay, this data is filled here. Okay, now the output of this one is connected to this one. The output of this one is connected to this one. The output of this is connected to this one, and we will take the output here. Okay, so therefore the data input is actually here. It is shifting from right to left side, and it will take the output in this way. Okay, so therefore this is what happening here, from here to here, and here to here, and here to here. This is from here to here, and here to here, and here to here. Agreed? That's what we are doing. So parallel loading, that means the holding information means we have to select S0. So it allows only this particular data. Okay, that means whatever this value is there, just a feedback connection, nothing else in it. This will say that this is a feedback connection. It's simply a feedback connection. It's simply a feedback connection. Feedback connection. Okay, this is what happening here. Okay. First of all, I want to write structural modeling for it, because somewhat it is look different, because in the previous cases we have seen only same type of components that we have used, but here two type of components are there. One is multiplexer, one is a D flip-flop. So we have to write the multiplexer and D flip-flop separately, and we need to call into your main program. Okay, so therefore yeah, before going to that one, I will do this one also. SR SL. Okay, that's it. And of course, don't forget about to write this clock signals for the flip-flops, for the clock signal, as well as there is a reset signal as well. So these signals are also there. Therefore 4-bit USA. So it is USR underscore 4-bit. Universal shift register of 4-bit size. Okay, this is the top level module. Okay, so what is the inside of this module? Okay, so for your sake of understanding, I will write again the same diagram. Please follow if you are not understand previously. So we need to have one multiplexer is required here. So this is the usual symbol that people will use to write. Okay. So the output of this one is connected to input of this one and produce in this way. Okay, so this is required for 3 times. Copy, and then I want to paste it here. Okay, and then paste again. This is the 3rd bit. This is the 4th bit. Okay, I hope you understand. Yeah. So it is very important to note that we need to have the output is called Q3 here, MSP position. This is called Q2. This is called Q1. This is called Q0. Okay, no. So the selection lines for each and everything is the same. Okay, the same selection line I'm using. So I'm using it. So this is also one usual way that we can write, but because of the same selection line. But please remember that it is a 2-bit size. It's a 2-bit size cell we need to write. Okay. Okay. So it take only one input at a time. Either it can take one signal, second signal, third signal, fourth signal. Okay, so like this, we have to provide 4 signals for each and every multiplexer. Okay, 1, 2, 3, 4. Okay, it's a D flip-flop, for example, D3, Q3, D2, Q2, D1, Q1, D naught, Q naught. Okay. Now, yeah. So it is mandatory to know that each and every flip-flop has got a clock signal as well as a reset signal. Every flip-flop has got negative edge triggered flip-flop. So it is connected here, it is connected here, it is connected here, it is connected here. So these fundamental circuits are very important to you to write your the project works. Whenever you are doing some kind of projects, this way of writing the code and way of designing the circuit is very, very important. Okay, fine. Now, only available output, externally available thing here is that we have only D3, we have only D2, we have only D1, we have only D0. Okay, and one more thing is that for shift right operation, again we need to know that SR is required here. Okay, here also we need for third case, right? For third case means this one is required. SL is required. Okay, so this is what actually you please remember that this is what inside of your module. Okay, so this is what the outside of the block Q2, Q1, and this is called Q0, right? Agreed. So I'm saying that this is a black box. Okay, so this green color is a box. The box consisting of the first one is selection line. This is the selection line, and this is DR, and this is SR. These are the external signals. You can see here this is an external signals. Okay, so outside of the box, all the red symbols are related as all the red symbols are external signals, remaining all internal to the circuit. Okay, so what are required here now? What input is required from here? Required here at this point? As we know that this last one is actually holding information, right? So the holding information is I can place here is this one is connected directly from here to here. Okay, better I'll use another color. From here to here, it is connected for the holding of the information. As you know that this is very important. Okay. What needs here? It needs this signal, right? So this signal is required here at this point because the shift writing operation. So this signal is required here. I think better I need to write the same color because these two are equal, right? So this is also connected at this point. This is also connected at this point. This is also connected at this point. Okay. Now what about here? Green color. So the output of this one is connected, this one need to be connected at this portion, right? So this is connected here. Okay, so the output of this one is connected to this one is connected at this place. Okay, the output of this one is connected, this one is connected at this portion. Okay, so only thing is that I have whatever I have written here the same way that I followed here, but remember that these are very important one. Okay, now so if you want to write a structural modeling for this, first of all I need to write the 4x1 multiplexer module and the D flip-flop module. So earlier I have written the multiplexer module, right? So just I want to copy without wasting my time. Okay, because so many times we discussed about those. It's a 32-bit size. This is not 4-bit is required. Have we done this 4x1 multiplexer before? Yeah, 4x1 multiplexer I have done here. Okay, that I have written in that behavioral modeling. Okay, it's not a problem. Okay, so this is what actually I have done previously. Okay. Okay, so this is what the modeling. So yeah, 4x1 multiplexer can be written in n number of ways, as we know that. Okay, it may be a structure modeling, behavioral modeling, and data flow modeling. Also, we can do it. But just I have followed here is a simply data flow model, behavioral modeling. That means it has got 4 input signals: 1, 2, 3, 4, and this is the selection output is, and this is the selection line. Selection line is also 2 bits I have used: S0, S1. This is I0, I1, I2, I3. Okay. Okay, fine. Now again, what is required? D flip-flop is also required. So I take the D flip-flop from the previous class only. I would like to take the D flip-flop. Yeah, this is what I can take. Negative edge trigger D flip-flop is required, right? So I have taken the D flip-flop here itself. I can paste it here. Okay, so what it is required for this one? This D flip-flop consisting of negative edge reset, negative edge clock reset, as well as clock, the Q, and it is DAN. It's a D flip-flop, right? Agreed? So this is the multiplexer, this is the D flip-flop. Related diagrams I have drawn. Okay, these are the essential components are required. Okay, now I want to make this top level module. So okay, copy, and I want to paste it here. I want to paste it here. What is the inside of the circuit here? Here we have. So this is what the inside of the circuit, right? So according to the structure only, we need to write the program. Okay, without this structure, when you write the program is meaningless thing. Okay. Okay. I want to make this one very smaller size for it to look better. Okay, fine. Okay, fine. Now let us write a structural program for this. Okay. Please follow this structure and so many bigger circuits that we have to do according to this structural modeling only. Okay. So let us write a module. Okay, better I have to take. Okay, module. It's a USR underscore 4-bit is the name I have given. What are the components are there? Here we have SR, SL, D, clock, S, RST, and these signals are there. Okay. Okay. So better I would like to consider the vector notation. Okay. Instead of taking all these things, I want to write it as a vector notation. Okay. So to reduce the complexity, it is a 4-bit size Q. Okay. Okay. We have a D input signal. We have a clock signal. We have reset signal. We have S signal. We have RS signal, SL signal, and Q signal. Okay. So these are the things are there. So out of all these things, inputs are, what are the inputs here now? First, let us write single bit size. Okay, I think it's better to write in that order only. So first, a single bit size I will write. Later, I will go for multi-bit size. Okay, so that's good idea. So first, I will write like clock signal, RST, SR, SL. Next, 2-bit size, the 4-bit size, the output. That's a good idea. Okay. Now the inputs are nothing but clock, RST, SR, SL. Okay, these are the single bit size. 2-bit size is input. Okay, it's better to all are small letters only, but SR and SL I want to write it as a capital letter. Not a problem. Okay, you understand the problem. Understand the situation. Okay. Next, 1 down to 0 of S is required. Okay. Next, another input is also required. 3 type of inputs that we are looking at. Okay, 3 down to 0 of D also. Okay, so first input is a single bit size, second is 2-bit size, third is 4-bit size. What about the output? Output 3 down to 0 of Q. Since I'm writing a structural molding, Q cannot be a register data type. Cannot be a register data type. Okay, it will be simply a wide data type. Okay, fine. Okay, fine. Now, so what is the first thing? I need to call multiplexer. Okay, so please remember that this is what I'm interested to write. Okay, this multiplexer. How many are there? 4 multiplexers are there. 1, 2, 3, and these are the 4 multiplexers. That means 4 times I need to call this program. Okay, so I want to call this program 4 times. Copy, and I want to paste it here. See, one important point we should remember. Okay, so from this diagram, what we understand that first 4 are the inputs. Okay, second 2 are selection lines. The last one is output. That's what the notation is. Okay, clear? Okay, that means 4 input signals I need to write here. So for that one, what I'm doing here, I need to modify the circuit according to my logic diagram. So this is called module 1. Module 1. Okay, so how do I modify this one? What is I0 for this one? First multiplexer. You consider the first multiplexer. The first multiplexer is connected with, what is the first one? D3. What is the second one? SR. What is the third one? Q of 2. What is the fourth one? Q of 3. Agreed? And it will produce, what is it will produce? So here we are talking about, what is it produce? We don't know, there is no name for that one. Let us Q. For example, it's a T1. So let me consider this is a T1. Okay. Inside of the circuit, I will write the green color, for example, T1. For example, T1. It is T1. What is the selection line for this one? Yes. Yes. See, in this top module, it is represented as a single bit size, but a single line, but having 2-bit size. Okay. So, but it requires two separate lines are required. So therefore, it's very important to note that it is S of 0. It should be S of 1. Okay. That means whatever the definition that we have done here. So whatever the definition that we have done here at this point, that means two signals are required. That means even though it is represented in the main module by a single line having two lines, but we should separately define like this. Then only port declaration is possible. Otherwise, if you're writing it is only S means, sorry, if you're writing only it is S means it is not valid. So the 4 lines that we can write it here, and the single bit we are writing here, and this is also single bit, but it is not port mapped. It is not at all mapped. Individual lines are required. Whatever the way that we have defined, the same way we have to take the signals from the top module. Is it clear to all of you? Please respond by the chart using the chat box. This concept is clear to all of you or not? Please respond, students. Yeah. Thank you. Okay, fine. Okay, now I would like to change these parameters. First of all, I would like to write these input and output, all other things, right? What is the first thing that I have to write? Q D of 3. So D of 3 is required. Okay, what is the next input? SR is required. What is the next input? Q of 2 is required. What is next is required? Q of 3 is required. Okay, followed by selection lines. S of 1 is required. S of 0 is required. And what is the output? T1 is required. T1. So this is how we need to write. Understood? Okay. So this is the first multiplexer. Similarly, we need to write for the second multiplexer. So just to copy this statement, another 3 times, copy, and I want to paste it here. Copy this, paste time. Copy this again. Okay, so these are the 4 times. But it's very important to note that unnecessary things that we have according to the second multiplexer. So let me call this is M2. Okay, this is called M3. This is called M4. So this is called M1. So this is the first one is M1. This is the M1. Okay, where should I write this name? So inside of this one, I'm writing M1, M2, M3. This is M4. Okay. So can you write what is the second M2? What are the inputs for the second M2? Anyone from the class, can you please type it so that I understand? I will understand that you will following the class. Please respond. Write it for M2. What is required for M2? What is for M2? M2 requires 2. Second bit is coming here. D2, Q3, Q1, Q2. Thank you. That's right. So this is called 3. This is called 2. S1, S0. Let me call this is T2. Okay. Therefore, this is called T2, for example. This is called T3. This is called T4, for example. Okay. Is that right that you have written? Let me check. D3 is correct. Yeah, I put wrong. So you are correct. Student, you are correct. So instead of this SR, I need to write Q of 3. Yeah, thank you very much. Q of 3, Q of 2, Q of 1. And the next one, I need to remove this one also. It is the Q of something. Here I need to write Q of 1. This is for 2, 1. 2, 1 and 3, third one. So first D1 will come into the picture, and the second one is DQ2 will be there in it. Yes, fine. And the next one is Q0 will be there in answer. Q0 will be the answer for this. So like this. Next one is Q0. Yes, we can remove. This is called Q of. Yeah, it is a Q of. What is this value? Of 1. Q of 1. Q of 0. But this should be M2 for M2. Third one is Q of 1. 1, 2, 3. So third one, right? M2, we are talking about M2. What is these things are there? DT is coming here. Okay. Next, the Q3 is the here. Next, Q1, kada? So what is this position now? So the last one, we know very well that this is the Q2. This is called Q1, I think, right? Q1. Yeah, Q1. Q3, Q1. Right. That's true. Yeah, Q1. I hope this is called Q1, right? D2, Q2. This is called Q1. No. This is called, what would be the case? That's the reason why we have to keep the information very clear. So this information will come and sit here for the right shift operation. It is coming from Q1. Yes, that's true. That's a Q1, not Q2. It's Q1. It's Q1. Okay. What about third one? Therefore, this is called Q2. This is called Q2. Yeah, this is actually Q1. It is easily to know that this is the Q1. This is actually, what about third one is correct or not? Q2 will come into the picture. This is the Q0, right? This is the Q0. Fine. Now what about this one? D0 Q1, D0 Q1, and this is SIN, right? SL. This is SL, and this is called Q of 0. I hope I have done correct. Okay. It's very, very important when you are doing the structural modeling. We have to identify that where the signals are coming properly. We have to set. Otherwise, there is a problem of erroneous output. Okay. So when you are writing the program and you do some kind of logically, so whenever we are following the same port mapping, the circuit will be connection is correct only. But you cannot get the expected output because instead of one signal will go to the one line, it may not go to that line. So it will go to another signal will attach to that one. In that situation, you will get wrong output. The connection is right. Logically, that is right. Logical connections may be right, but you may not expect that the output is correct. Okay. So please be careful about it. Okay, next, similarly, I have to take, similarly, I need to take D flip-flop, right? Where is the D flip-flop? Yeah, this is the D flip-flop. Have to consider here. It's a D flip-flop. What inputs that I need to write here? It is called M5 that let us write. Okay, so M1, M2, M3, M4 already I have used the names, so should not use the same names. So the first MSB is M5, for example. Okay, here what is required? First D input is required. What is the D input here? What is the D input here now? It is nothing but T1, right? It is nothing but T1. RST is the same. Clock is the same. What is the Q for the MSB bit? That means I'm talking about this one. Please remember that I'm talking about this flip-flop. Okay. So for this one, what is required? Q of 3. So this is required for us. So instead of doing this one, I have to take this one. Therefore, fourth assignment will be done properly. Okay. So I have to copy this one for another 3 times. Okay. Okay. Paste here. Paste here. Paste here as well. Okay. So please remember that these are 6, 7, and 8. So instead of taking this one as T2, T3, T4, here is 2, 1, 0. Right. Finally, we need to write end module. That's it. That's it. Finally, we need to write end module. So this is all about the program. How many modules are here now? You can see here. As you can see here, it's the module for a top level module. This is the subcomponents. These two are subcomponents. Okay. Okay. So there is a possibility of writing the multiplexer differently. Okay, because multiplexer is also is not a fundamental element. Okay, we can write it in any modeling style. Okay, so just you can suppose if you feel that this is a very big representation, then go for a simple data flow modeling. Okay, it's a very simplest one. So then you can call. So what is the inside of the multiplexer? It doesn't take does not have any impact. Okay, the thing is that whether we are taking the same multiplexer into your main module or not is very important. The port assignment should be takes place. So as you can see here very carefully, so how many ports are there here? 1, 2, 3, 4, 5, 6, 7. 7 ports are there. Here also we can say that 1, 2, 3, 4, 5, 6, 7. 7 ports are there. For example, so there may be a possibility of something here. Yeah, positive edge also we can use it, provided this particular flip-flop, whatever the top module is there, in this top module, if you are using the negative edge, then we have to use the negative edge flip-flop only. Okay, so if this top level consisting of positive edge triggered flip-flops, then you have to define the positive edge flip-flops. So in this one, you have to change it in this program. In this program, you have to change the positive edge. Okay, so therefore that's depending upon the what are the components are there in the top module is important. According to the top module, according to the top module component, we have to define those components, right? Okay. Now what I'm saying that here is for example. So for example, I am writing the instead of saying that this is the scalar notation I have used. Instead of that one, I'm using the vector notation. So it's a 4-bit size of I am considering here. Y is also having 2-bit size that I am considering here. Yes. So then how the module declaration here, something like this, module. Okay. So please remember what I'm trying to say, module mux, for example, and I comma, S comma, Y I'll write. So what will happen? I will declare here is S is 4-bit size, S is 2-bit size. It doesn't matter. But whenever I'm calling this one, okay, whenever I'm calling this one in here, for example, here, if I call this one, what will happen? I need to write only yes here. I here, yes here, y. Okay. Port mapping is there, but actually what is happening here? But I is not a 4-bit size directly. So I is a variable quantities. One is a 1-bit is a d of 3, second one is s of r, third one is q of 2, fourth one is q of 3. So both are different one. So in that sense, writing this vector notation is not meaningful one. Okay. Instead, if you want to, sir, I want to use only this one only. For example, I want to use this one only. But how do we modify this mux underscore 4+1 in that way? So then what I have to do is that very simplest method. So I have to use the concatenation between these two, these three, these four. So whenever I movement, if I'm writing the concatenation, this is equivalent to say that it's a 4-bit size I. Agreed? Similarly, 2-bit S is actually also I can put it in the vector notation. These 2 bits are equivalent to say that 2 bits are vector notation of S. Y is actually a single bit, it doesn't have any problem. Is it clear to all of you? Please respond. Yeah. So students, one of the friends says that we need to have T1, T2, T3 signals need to be declared. Yes, it is required to declare. I forgot that one. Okay. So please try to write here is while T1 comma T2 comma T3 comma T4. Right. Very good. Yeah. So whatever the concept that I have discussed here, is it clear to all of you? That means whenever you are declaring something, the same way that we have to use in the top module also, according to the variables that is present in the top module. Okay. So it's a very, very important one. So I don't want to use this for the time being. Just I want to remove these portions. Okay. Please remember that point. It is an additional information. Okay. So this is how we have to do it. And if you want to test this top module, what I have to do? If you want to test this module, what I have to do? I have to define the D input, clock input, S input, RST input, SR input, SL input, right? That is how to do it. So I have to define all these things. Meaningfully, we have to write the test bench for it, test waveforms, and from that one, we have to describe it. Okay, please try to do it as a homework. Okay, and okay, so the structural modeling requires these many number of this much labor is involved in it. Okay, so let us try to do this one, the behavioral modeling, in a very easiest process. Okay, so let us try to do the thing in the behavioral modeling. Okay, so how do we do this one? What is the functional table for this one? So module, so behavioral modeling. Behavioral modeling. So how can I do this? Simply let us write very quickly. Okay, so what is the functional table? Functional table is nothing but a reset signal. Okay, RST, clock, and D input selection line, D input, and SR and SL. Okay, for example, something like this. Okay, if the negative edge of the reset is there, irrespective of any other things, the Q value will be equal to all 4 zeros, 4 bit of all zeros. If it is other than this negative reset, for example, if we find that negative RST, for example, then if the selection line is equal to 0, 0, okay, whatever the D input is there, the D input will, whatever may be the assigned R, D input will be assigned to this one. If it is the other information, if it is a negative edge, 0, 1, if it is whatever it may be the D input it is, for example, SR is equal to, for example, 1, it may be 0, for example, whatever it may be, it doesn't matter. In fact, it doesn't matter. Then what will happen? This is SR will come here, and this is called Q3, Q2, Q1 will be the answer. Other than this one, whatever it may be, it is 1, 0, whatever it may be this one, whatever it may be this one. If it is 1 means I can simply write it in SR. Okay, SR maybe logic 0 avvachu, logic 1 avvachu. Okay, it is SL. Manam ఏది ఇస్తది? Sorry, SL. Then this is called Q2, Q1, Q0, SL. Okay. So what about the other cases of RST? It is a negative edge 1, 1. Irrespective of any other things, it will be Q3, Q2, Q1, Q0. Ante kada? Agreed? So if it is another case, it is also another case. Whatever it may be these things, it will be the again also the previous values only it will hold. So these two things are the same. Okay, this is the functional table. Okay. Now let us write very quickly Verilog program for this. Okay. So please wait for 2 minutes. I will complete it and you can leave. Okay, just it will take another 2 to 3 minutes. So let us start here. Module USR underscore behavioral. Okay, its values are clock. Okay, better I'll take this declaration part. Okay, I don't want to write all the thing. Copy, I want to paste it here. Okay, okay. What is not required, instead of taking this one, I want to consider this one, behavioral modeling. Okay, meanwhile I need to remove this one. I can keep this here. Okay. Okay, so what is not required? This information is not required for us. It is completely related to structural modeling. It's not required for us. Okay, agreed? Okay, remove. Okay, why it is required? We have to select all and must be delete. That's it. We have to use intelligence sometimes. So it must be a registered data type. So very important one is it is a registered data type. Now we need to write always statement. Always at the rate of negate of reset, negate of clock. Okay. Okay, fine. Now I'm going to write case statement. So instead, in the previous cases we have used the if statement. Okay, of course if we write in the if statement only, we write the if statement only. So later we'll go for that one. Okay, if not of RST, what has to happen? QL is equal 4 bit of all zeros. Okay, fine, that's good. Else if S equal to 2 bit of 0 0, then what is happening? Then the Q is equal to assigned by D signal. Agreed? I hope you understand this concept. Okay, so this is also okay. Sorry, this is a keyword, right? Okay, so I want to copy this one 4 times. According to this one, I'll write copy. Paste it here. What is this? Paste it here. Because the 4 combinations, S has got 4 possibilities. Okay. So that's the reason for each and every possibility I'm writing this one. So now it becomes, it is 0, 1, for example. It is 1, 0. It is 1, 1. Okay. So for these cases, what about the first one, the second one? Right shift operation. So as we have seen in the previously, concatenation operation. Concatenation of SR and a Q of 3 down to 1. That's what we have seen previously. Okay. Similarly, we'll write here is actually concatenation of Q of 2 down to 0, and this is called SL. This one. The last one is Q itself. Q. If not writing the else statement, for example, we haven't write any kind of else statement here. That means this is what will be executed. This is what will be executed. Okay. So that's it. We have done everything correctly, and this is how we need to write the behavioral modeling for the universal shift register. Okay. Okay, please try to write this one properly, otherwise you will confuse. So it is 0, 1, it is 1, 0, it is 1, 1. So this operator is called the equality operator. Equality operator. If you are writing the single equal, if you write a single equal, suppose for example here we are writing the single equal. This is assignment operator. It is called blocking assignment. This is called blocking assignment. So please identify that double equal is there, equality, that is the comparison, but whereas single equal requires blocking assignment statement. Okay, so this is how we have to do the behavioral modeling module. Okay, we stop it here today, and we will see the remaining things in the next class. So another class is required for the counter, and then go for the finite state machines, and some theoretical parts required. So it will take another 3 to 4 classes to complete the first unit. Okay, so thank you very much for your patiently listening the concepts. We stop here today.